Okay, so let's start playing around with waves and particles so that we can build a mathematical description that captures the results of the following experiments. So let's start with creating waves, and a simple way to do this is to imagine water. So imagine that we have a pool and that we drop a rock. So here is a rock. This is a rock, and we drop this rock into the water, and it creates these ripples that we're familiar with, something like that, and they sort of move outwards in all directions. And now let's imagine that we have a little barrier here, but that the barrier has some holes in it. And in fact, two holes, right? So water can pass through here and through here, except we're going to close this hole off, so the water cannot pass through there. And the water will only pass through the upper slit. And when it does that, it seems to behave similarly, such that we get ripples moving outwards from that hole. So something like this. And if we stand back here, we will always obviously feel the water. We'll get wet. So this represents sort of a screen where we can detect the amount of water that reaches us. And so we can sort of say, well, what's the degree of wetness? How wet do we get? Or the intensity, the wetness, or the intensity of the water that reaches us. Well, it's kind of, this is sort of the place right behind the hole where you'll get most of the water, and as you move away this way or that way, you'll get less water. So it kind of looks something like that, where it peaks somewhere around there. So there's nothing terribly surprising there. Let's say that we do the same thing. Here's our rock. We drop it into the water, and it creates these ripples, just like we saw before. And we just do the symmetric situation where we close this slit, and we let the water pass through this hole here. Of course, we'll get a symmetric situation. We'll just shift the intensity down to the other slit so that most of the intensity is associated with the region right behind the slit. Okay, so this is sort of the wetness. But now let's imagine that we drop two rocks. So we have something like this, and we have our little ripples that are created, and they move outwards like that. So that we create new ripples behind each slit. They're both open. All right, so we'll get something like that. And let's maybe make this one red. So here's I guess a red rock with red ripples. And so here we'll get something like this. Something like that. And here is our screen. So what is the degree of wetness at each point? Well, the greatest wetness is right behind this point where there is no slit. And it's symmetric, but there are places where you get no water. So, and then it decreases like that, and it's perfectly symmetric on this side. So it looks like that. So that's a classic interference pattern. Okay, so we call this interference or wave interference. So that's a telltale sign of wave behavior. So now let's consider the way particles behave, which is different from this. So here is a source of particles, and we launch our particles toward the same holes in a wall, in a barrier, except we again close one barrier off. Well, what kind of a pattern do we get? So the particles can come through here only, and when they come through here, they can distribute themselves in random ways. They can sort of hit the barrier and get knocked to one side. But overall, right, so it could hit here, it could hit here, here, and it's unlikely to hit further away. And you get a distribution where the intensity sort of peaks behind the hole. Okay, so this is intensity of where the rocks are hitting. And of course, if I do the same thing, but leave the other slit open, so I'm closing this slit, then I'll get a symmetric situation where, because these are particles, I'll get a hit somewhere. I could get a hit there, a hit there, a hit there, and so on. But overall, the intensity sort of peaks behind the hole here and dies off as you're moving away. And so if we then imagine doing the same experiment, except we now make sure that both holes are opened, then we'll just get the sum of these two peaks. Something like that. Symmetric in that respect. Okay, so those are wave and particle behaviors. So now let's imagine doing an experiment where we play around with electrons. So we somehow take electrons and we want to figure out how they behave and see whether they are more like waves or more like particles. In the modern physics course, we saw that they clearly behave like particles in certain respects. And here we'll get a sense of how they can also behave like waves. So here are electrons. I'm kind of drawing them as if they were particles. And here is our double slit. And let's close one of the slits off. And what pattern do we observe? Well, we'll observe a pattern that is not really surprising to us, something like that. And so these are electrons. They seem to behave like particles. Now let's do the symmetric version of this. There's nothing surprising there. We'll get a pattern that has a peak behind that hole. But now let's do the same experiment. keeping both slits open? Do we get the pattern that we expect, which is two peaks, these two peaks added together? And the answer is no. We get the greatest amount of electrons hitting here. So, electrons will hit in different places, and we'll get a pattern that we're familiar with, but it's not the particle behavior. It's a wave behavior. So the question is, are electrons waves? Right? This clearly suggests that electrons have wave-like behavior, but we know that electrons also have particle-like properties. So these drawings suggest that we are launching a bunch of electrons. So let's try to be a little more subtle in our experiment and launch individual electrons. So we can do that as well. So here is an individual electron that we launch at the double slit. And if we close one slit off, then we'll see that in fact it behaves like a particle. So the electron, if it gets through, in other words, it goes through this hole, it could hit, say, there, or it could hit there, or it could hit there. It's unlikely to hit anywhere too far away from here, or too far away from here in this direction. And so we'll get an intensity for the hits that looks something like that. And if we do the same thing, so this is one electron. Right, we launch one electron and we see where it hits. If we do a symmetric version of that, the electron could hit here or here or here. So the electron does behave like a particle in that it does hit somewhere and we can detect it. But overall we'll get a distribution which peaks behind the second slit. But the weird thing is that if we do this experiment, here's one electron, and we keep both slits opened, it's not the sum of these two peaks that we get, but we get the peak here, which is the kind of thing we're familiar with from wave behavior, the standard interference pattern. So it's a little strange that this happens with one particle. So we have discovered that we need a combination of, in some sense, mutually incompatible properties. Both particle and wave-like behavior have to be captured in our mathematical description. And so here is a wave-like quantity that can describe these waves that come through the slits. And we have wave numbers and traveling wave features, right? But we also have particle behaviors that connects, in this case, the angular frequency to the energy. And we saw this in the modern physics course, the wave number to the momentum. Right, so these are wave-like quantities, omega and k, related to particle-like quantities, energy and momentum. And so we need this kind of a thing to explain the behavior of particles at the subatomic scale. And the question is, what does this kind of thing mean physically? And we want to derive an equation that allows us to derive this kind of thing for various particles in different situations, and that'll lead us to the Schrodinger equation. And that's the beginning of quantum theory.